Let's go, let's go, let's go. कैसे हो भाइयों? इसको बल को काटो। ठीक है, अब ठीक है। कैसे हो? फाइनली भाई आज कर रहा मन इसको खत्म कर ही देने का।
N minus one comparisons. Why? Because I started over here where there are 8 humans, and I looked for the smallest element, and I did so by comparing them. N elements, a total of n minus 1 times to compare them ultimately. So that's n minus 1 steps the first time. But that got me to having 0 in the right place, so then I had 7 steps, and then 6 steps, and then 5 steps, and so forth. So if I generalize this with n, instead of worrying about the specific number of human volunteers we had, that's like saying n minus 1 steps the first time, plus n minus 2 steps the second time, plus n minus 3 steps the third time, plus ... plus finally 1 step when I'm all done solving the problem. So how can I sort of work this out? Well, if you remember like the cheat sheet at the back of your math book, a series like this actually sums to n times n minus 1 all divided by 2. And sort of trust me or take that on faith, but that's what it equals. Now we can sort of apply some high school style multiplication. So we've got like n squared minus n by distributing the n all divided by 2. And if I multiply or if I divide that out, I've got n squared divided by 2 minus n over 2. But here's where asymptotic notation is our friend. I don't really care at the end of the day precisely how many steps selection sort takes. I want to know on the order of how many steps it takes. Why? Because again, I might have a fast computer or a slow computer. What I really care about is when n gets really big, what really impacts the performance of this algorithm? And I dare say that if you take a really big number and square it, that's a way bigger deal than just dividing by 2 or dividing by 2. In other words, the highest ordered mathematical term here is the n squared. That's the one that's really going to matter when we're talking n equals a million, a billion, a trillion. That's going to dominate all of the other characters. So if I use my asymptotic notation to describe the upper bound on the running time of selection sort, it's on the order of n squared. I don't really care about the precision when it comes to describing running times. So n squared, it's a lot, and you can see it visually with that visualization. All of the pink, all of the pink, all of the pink is because we were doing so many darn comparisons again and again. So is there a categorization we can do here? Well, with selection sort, it would seem that in the worst case, that algorithm might take us as many as indeed n squared steps. But what about the best case? What about the best case here when it comes to selection sort? Well, could it be omega of 1? Could we get away and just get lucky with 1 step to sort the thing? Would it have to be more using this same code? Well, consider then these doors here as being, again, representative of exactly what's been sorted. Could we get away with omega of 1? Or would it have to be something more? Well, here's that same cheat sheet as before. Does anyone want to conjecture, other than the person with whom I had a chat during the break with, as to what the lower bound on the running time of selection sort might be? Maybe n squared. Why do you say that? Yeah, really well said. Even in the best case where the numbers just happen to start sorted, which could happen in some perverse scenario, the source code doesn't take into account that being possible. In my pseudocode here, there's no allowance for, hey, by the way, if array is already sorted, exit or quit early. Instead, it is going to blindly do this n minus 1 times and then do this and then do this blindly. So literally, if I had 8 volunteers come up and they sorted themselves in advance, 0 through 7, I would have taken the same number of steps, even though nothing interesting would have been happening, at least according to this source code. We could clearly come up with better source code that is written in pseudocode to solve that problem better, but at least as written, it does not do any better than that. So we would say that selection sort is in big omega of n squared. And now just to bring in the other Greek term, the capital theta, if we have upper bound of n squared and lower bound of n squared.
2 मिनट रुक जाओ, मेरे को कुछ चीजें कर लेने दो, उसके बाद ध्यान डिस्ट्रैक्शन हट जाएगा पूरा कंप्लीट. फोन फेंक दूंगा बगल में. Yes, me of course. मेरा दिमाग कुछ नहीं कर पा रहा. वैसे your idea was good. मेरा छोड़ अपना बता. सो जा रात भर हो या सुबह इंस्टाग्राम देख ले, कुछ ना कुछ तो मिल ही जाएगा। भाई को बिल्लियाँ पसंद।
कितनी लड़कियों को पता है लड़कों
महंगा ये सब क्या बोल रहे
कितनी लड़कियों को पता है लड़कों का जी स्पॉट किधर होता है गेम में अंशुमान
हैं? बंद करते हैं इसको। रख के आता हूँ, गर्मी लग रही है मेरे को, पर फिर भी मैं स्ट्रीम कर रहा हूँ।
हाँ, आज भी नहीं हुआ।
You can also now conveniently say that selection sort is in theta of n squared because they're one and the same. It's just a third term we can whip out. What about the second algorithm now? Like, clearly, if it was the second algorithm I proposed, maybe it is, in fact, better in some way, and not just because it might be a different way of thinking about the problem. Maybe it's better design. Well, bubble sort similarly treats our volunteers as this array from element 0 to n minus 1, and here might be the pseudocode with which we could capture what we just did. Though I'm going to simplify a little bit for the sake of discussion, and I'm going to tolerate some of the unnecessary footwork of going back and forth simply to keep the pseudocode simple. But I'll stipulate that even if we were to optimize it a little bit vis-a-vis this version, turns out that asymptotically it's still going to be in big O of the same thing, but we can do a little better on our lower bound. Repeat the following n times, just like Scratch. For I from 0 to n minus 2. So in other words, if you think of our human volunteers, I might be my left hand pointing at location 0 first, and then I want to compare each pairwise person. So I want to compare person I to person I plus 1. And that's what's really going on here. If numbers bracket I and numbers bracket I plus 1. So if the person my left hand is pointing at and the person my right hand is pointing at are out of order, then go ahead and swap them. But I do this a whole bunch of times, it would seem. I repeat this n times, and then inside of this loop, I also iterate from 0 to n minus 2. Well, why is that? Well, n minus 2. We don't normally talk about n minus 2, but if I'm comparing my 8 humans and sort of walking down the array like I was, I want to make sure that my left hand does not go to n minus 1, because n minus 1 is always the last person, so where would my right hand be pointing at? Sort of empty space. So I need to be careful, and if I'm comparing things side by side, I want my left hand, to go up to n minus 2, the second to last person, the second to last element of the array, so my right hand doesn't go over the end of the array itself. So subtlety, but that's why I tried to call it earlier, the n minus 1, n minus 2, just to give you a mental model for that. All right, so technically speaking, we can optimize this a little bit, and if we really get into the weeds, I only have to repeat this n minus 1 times. Why? Because once I get to the end of it, like the last person is sort of naturally sorted already. I don't have to worry about fixing one person. They will have bubbled to the right location. All right, so if we have this list of numbers, just as we had our array of volunteers, how can we think about this visually? Well, left hand is I in the story, right hand is I plus 1, and what did I do? Again and again and again, I compared them, and if 7 and 2 are out of order, I swap them. 7 and 5, swap them. 7 and 4, swap them. 7 and 1, swap them. 7 and 6, swap them. 7 and 0, swap them. 7 and 3, swap them. And notice, just as with our humans, 7 bubbled their way up all the way to the end, leaving me with 7 more problems to solve, but at least I took a bite out of the problem. And in fact, on the next iteration, we would sort of come back and start over, but strictly speaking, we don't have to go all the way to the end this time. So bubble sort fundamentally sorts the array, but does it do it any faster? Well, here is how, again, we might write pseudocode like this, and let me propose 2 ways of thinking about the bubble sort running time. It turns out when you have pseudocode in front of you, or in the future, actual C code or actual Python code, once you have an eye for it, you can literally look at your code or someone else's and reason through how many steps each line of code should take. So for instance, how many steps will this first line take, where you're repeating something n-1 times? Like this one's kind of a gimme. It literally will take n-1 steps, because it's just saying what it is. All right, what about the loop inside of this loop? And technically in C, you could use 2 for loops, you could use 2 while loops. I'm just using English vernacular that is kind of simple as possible here. But what about this? For I from 0 to n-2. Well, this is technically a total of n-1 steps, because if you start at 0, and then 1, and then 2, and then 3, all the way to n-2, you have counted a total of n-1 times. So the outer loop, by this analysis, is going to take n-1 steps, but every one of those interior steps is going to take n-1 steps, so there's some multiplication going on here. Do this inner loop this many times, but do that this many times too. And now, how many steps does it take to check if 2 numbers are out of order? Well, that's just like comparing 2 numbers, left hand and right hand, so that's like 1 step. And sometimes I swap them, and all right, swapping them means like this person has to come out, this person has to come out, then they have to swap, so that's like another 3 steps. So maybe this is like 1 step if we just kind of keep things simple. Maybe it's 4 steps. I don't really care. It's a constant number of steps. No matter how big this array is, I'll claim that you can swap people in constant time. Might be 1 step, might be 4 steps, but it has nothing to do with the length of the array. It's only going to take the same number of steps to do that kind of swapping. So now you can multiply this out. n-1 times n-1 times, to keep it simple, 1 or 4, whatever. I'm going to ignore that factor. We can then figure out how many steps this whole algorithm takes. In fact, if I sort of write this out as before, n-1 steps times n-1 times, that gives me, if I sort of do FOIL or whatnot, n squared minus 1 n minus 1 n plus 1, combine like terms, n squared minus 2n plus 1. And here too, like I don't really care about this level of precision. If I wave my hand out the details, this is on the order of n squared also. So to be clear, if we compared selection sort and bubble sort, technically they're going to be slightly different numbers of steps. But the reality is, if you run these algorithms long enough with big enough values of n, they're both going to be super darn slow, because the dominating factor is still n squared. Now I can do one optimization, in fact, but let's first consider what the upper bound is. In bubble sort, the upper bound apparently is on the order of n squared steps. But as written too, it would seem that this algorithm, as written, also is going to be omega of n squared, because it's never taking into account, hey, wait a minute, is the array already sorted? In which case, stop sooner. We don't have any language for that here. But what if I add a super simple conditional here? I could, after every iteration from left to right, just ask myself, did I make any swaps on that pass through the volunteers? If so, there might still be work to be done. But if not, why am I going to crazily repeat myself? Because if I didn't make any swaps one time, I'm definitely not going to make any swaps the next time. It's going to be stuck in some loop. So I can sort of short circuit my logic by just saying, hey, if no swaps on one of those passes, quit. You are done. And if I do this now, such that now I do maximally 1 pass, if the list is already sorted, to notice that the list is sorted, what could you say bubble sort's lower bound is, using omega notation? Omega of n. It has to take you at least n steps, logically, to figure out if the array is sorted. It cannot be omega of 1. Like if you're looking at 8 elements, let alone n elements, there is no way, logically, to take 1 step and conclude that all n elements are sorted. That makes sort of no sense, but it is indeed an omega of n, because you just need 1 pass to conclude that everything is indeed in order. So it seems that bubble sort is actually a little bit better. And let's see how it actually plays out visually. Let me go ahead and go back to my visualization from before. I've re-randomized it, and I'm going to click this time bubble sort. And you'll see that it's going to solve the problem in fundamentally with the fundamentally the same outcome, but notice that the work it's doing is a little different. The pink indicates now which two pairs of elements are being compared again and again. It's sort of non-obvious what's happening over here, but clearly the biggest numbers are bubbling their way up to the end of the array, just as our human volunteers. We had number 7, and then 6, and then 5, and then 4. But again, here too, you can see visually how many times we are retracing our steps to ask a different question, but again, touching or looking at the same elements in memory again and again and again. And this isn't even this many elements. What are there, like 100 or so elements here? Like, my God, this is taking forever to sort this many elements. Maybe this is why, then, if you just need to answer a question once, you just sift through the papers, find me the number 50, and don't bother sorting altogether. But if you sort it once, and then you have millions of customers like Google searching and searching and searching, maybe it's worth spending that time up front and then amortizing it, so to speak, over the lifetime of the data itself. Okay, I don't have to keep stalling, because now that algorithm has concluded. So to be clear, with that optimization and bubble sort, we can make it sort of better than selection sort, but ultimately it's going to be still on the order of n squared steps. Questions on selection or bubble sort or sorting more generally? Yeah? Oh, good question. What happens if I press bubble sort now, knowing that it is already sorted? Let's see if this visualizations implementation is the smart version with that additional conditional, or if it just goes back and forth and back and forth. Ooh, not well implemented. Notice that they are just blindly doing the first version of my code where there's no additional check. Did I do any swaps? Because even though you're seeing pairs of pink, none of those bars are actually moving. So this is both big O of n squared and omega of n squared, aka theta of n squared, aka poorly implemented in this case. Missed opportunity for them to have done this. I don't know if you need to be convinced that it's not going to do anything, but all right. It'd be like holding in a sneeze if we don't go to the end. Almost done, almost done, almost done, and no useful work was done. But it's now indeed sorted. All right, can we do better than selection sort? Can we do better than bubble sort? Yes, and there are dozens, hundreds, I mean maybe thousands of different sorting algorithms out there. And in fact, bubble sort and selection sort can be useful in the real world. I mean, I have actually in like research projects quickly whipped up in code an implementation of one or the other because it's just so relatively easy. Like first time through it, like you're gonna make mistakes, you're gonna have buggy code, but they're relatively easy algorithms that you don't have to think hard about. And in fact, sometimes it's faster to whip up a bad algorithm and just let the code run than spend more time writing a better algorithm only for it to be done like this. It's kind of a wash sometimes in the real world. But in practice, what we're going to find is you and I, except for something like a homework assignment, are not going to be in the habit of writing sorting algorithms anyway. We're going to use a library like a lot of those other functions, but you'll understand what algorithms are actually doing for you underneath the hood. So what is a technique we can bring to bear on this problem that might help us think about the problem a little bit differently and maybe help us solve the problem better? And by better, I mean, let's stop repeating ourselves by touching those elements again and again and again. Let's really try to minimize the number of comparisons we're doing, because that's what was getting computationally expensive in terms of time. So here, for instance, is an algorithm we've seen before, namely searching for things behind doors. So this was binary search. Same as before, whereby instead of looking for 50, I'm more generally looking for a number behind the middle door, or to the left of the middle door, or to the right of the middle door. Even though I didn't call it this earlier, it turns out that this algorithm, as we used earlier today, is an example of what's called a recursive algorithm. A recursive algorithm is one that calls itself, or put more plainly, in the world of C, and frankly in the world of mathematics, a function is recursive if it calls itself. Now, we've used main in C code, and we've called getInt. We've used main, and we've called getString. What if main called main, for instance? That would be an example of recursion, but generally frowned upon to have main call main. But we could certainly have another function that we write that maybe does call itself toward a useful end. So why is that? Well, notice that in this algorithm from earlier, binary search, it's already implicit that this search algorithm is using a search algorithm, because I left it unstated. Well, what does it mean to search the left half? Well, implicitly, to search the left half means shorten the list by half and then do all this again logically. Just apply the same logic to a smaller data set. And because when we went left or right or left or right, both this week and in week 0, because we kept shrinking the problem, it's okay if you keep doing the same algorithm again and again. The problem's getting smaller, so eventually you're going to have no doors left, or eventually you're going to find the number you're looking for. So these cases here, where you have very specific cases, like if there are 0 doors left, or if I found the number I'm looking for, those are generally what are called base cases, where the thing sort of bottoms out logically, and you get back an answer at that point no matter what. These 2 lines that I've highlighted are generally called recursive cases, whereby you don't get an answer yet, you have to do more work by generally shrinking the size of the problem and doing the same logic again. So a recursive algorithm or recursive function is one that calls itself, that uses itself, but hopefully on a smaller and smaller size problem. All right, so with that said, here is the same pseudocode from week 0, when I was searching the physical phone book looking for John Harvard, for instance, trying to call them if the number is there. Notice that in week 0, I actually used very deliberately a loop. It was not called that per se until we slapped some terminology on this algorithm, but I literally said, go back to line 3, go back to line 3. And then we said, you can call these things loops. And it means sort of visually you're going back and back and back. But this could be rewritten, this algorithm from week 0. We could do something like this. Instead of saying, open to the middle of the left half of the book, and then go back to line 3, which really just means search the left half, or search the right half, why don't we just say that? So let's collapse these 2 pairs of lines from week 0 and just say search the left half of the book, search the right half of the book. I can now get rid of the blank lines and kind of tighten the algorithm up, and now it's a shorter chunk of pseudocode, even though it's sort of left unsaid. Well, what do you mean 3? Which really just means search the left half or search the right half. Why don't we just say that? So let's collapse these 2 pairs of lines from week 0 and just say search the left half of the book, search the right half of the book. I can now get rid of the blank lines and kind of tighten the algorithm up, and now it's a shorter chunk of pseudocode, even though it's sort of left unsaid. Well, what do you mean search the left half? What do you mean search the right half? Well, who cares? I don't need to tell you how to search half of a book. I've told you how to search a whole book. So just use the same logic to search half as many pages, half as many pages, half as many pages. So whereas the previous version of this code here is an iterative version of our code insofar as it uses loops, this version now is a recursive version of that same algorithm. So sometimes you can solve problems with iteration, that is loops, or with recursion, and sometimes one problem is just better suited for one or the other. And among our goals in the coming weeks is to help you identify when you might want to use one technique or another, but generally iteration tends to be the more comfortable approach. But let's see this in context. There is, I've claimed, recursive algorithms, recursive code, as in here. There's also recursive physical structures in the world. Like here's that pyramid from Mario, this one being pretty short and of height 4. Let me get rid of like the distractions of the background. This physical structure is recursive in some sense. Why? Well, this pyramid of height 4 is really just a pyramid of height 3 plus one more layer of bricks. Well, what's a pyramid of height 3? A pyramid of height 3 is really a pyramid of height 2 with one more layer of bricks. What's a pyramid of height 2? It's really just a pyramid of height 1 with one more layer of bricks. What's a pyramid of height 1? Just a single brick. So that last statement is sort of a base case. At some point, I can't just keep like dragging things out and telling you how one is based on the other. At some point, I just have to say pyramid of height 1, it's just a single brick. Stop. But everything else can be recursively defined in terms of a pyramid of a smaller size. So if actually I want to do this implementation, let me actually whip this up in 2 different ways. Let me go back to VS Code here in just a moment. And in VS Code here, let's go ahead and make something called, say, iteration.c, just to make clear what kind of technique it is. So in VS Code, I'm going to go ahead and say iteration.c, and in this program, I'm going to write code that prints out a pyramid like this, of height 4, for instance, or anything else. So let me go ahead and at the top of this file include CS50.h, so I can ask the user how big it should be, include standardIO.h, so I can actually use printf. Let me go ahead and in int main void, just tee up the beginning of a program that's going to ask the user for a height of a pyramid using our friend getInt. And then I'm going to assume for the moment that there is a function called draw, whose purpose in life is to draw a pyramid. I'm going to pass in that height. Done. So this now invites the question, well, how do you implement the draw function? Well, a couple of different ways. Let me do it iteratively with a loop. So let me go ahead and define a function that doesn't return anything, because I just need to have side effects printing on the screen. I'll call it draw. It takes as input a value like n for the height that I want it to draw. And then inside of draw, what am I going to do? Well, this is easier than problem set 1 was because of the direction that the pyramid is heading. So this I can do fairly quickly as 4 int I is 0, I is less than n, I plus plus, and then inside of that loop, so that's going to give me row, 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 row. I want to now print out the number of bricks for a given row. Well, I claim with a quick glance, int j equals 0, j is less than I plus 1, j plus plus, and then in here I'm going to go ahead and print out a single hash. Then out here I'm going to go ahead and print a new line. So I did this super quick, but let me convince you that it probably is correct. Here I'm iterating from 0 up to, but not through n. So if I want a pyramid of height 4, this is like giving me the first row, the second row, the third row, and the fourth, from top to bottom, because that's how the screen scrolls. But then inside of each of those rows, how many bricks do I want? Well, on the very first topmost row of a pyramid, no matter its height, how many bricks do I want there?
4.
The very top, I just want one, the single brick. Well, if I start counting I at 0, I don't want to print 0 bricks, so I need to do a bit of arithmetic here. I need to do I plus 1. So 0 plus 1 ensures that this inner loop, j, gives me 1 brick, and then 2 bricks, and then 3 bricks, and then 4. So I just need to be a little clever and think about the arithmetic, but I think that gets the job done. That prints out hash, 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 one at a time, but at the end of each row, I move the cursor to the next line. So even though I did this pretty quickly, and it might have taken you much longer to do problem set 1 as expected, I think this will give me what I want, so long as I avoid making a past mistake. I need to put the prototype of this helper function at the top. So let me open my terminal window, make iteration, enter. So far so good, / iteration, enter. Let's do a pyramid of height 4. And it seems to, in fact, work. And I can do this even bigger. Let me do a pyramid, for instance, of height maybe 12, enter. And it seems to be working, indeed, with iteration. Well, what if I instead want to use recursion as a technique instead? I bet I can actually do that. Because, again, what is a pyramid of height 4? Well, it's like saying print a pyramid of height 3 and then add one more row. Well, what's a pyramid of height 3? Well, print a pyramid of height 2 and then add one more row. What's a pyramid of height 2? Well, print a pyramid of height 1 and then add one more row. The only problem that's interesting is how do you print a pyramid of height 1? Well, just print a single brick. So curiously, that kind of thinking will actually give us a fundamentally different solution. So let me do this. Let me shrink my terminal window and close iteration.c. Let me open a file called recursion.c just to make clear what technique I'm using. Let me include CS50.h at the top. Let me include standard io.h at the top, int main void again. And in here, again, int height equals get int, and then ask the human for the height. Then go ahead and call an imaginary draw function passing in that height, which doesn't yet exist. But now let's make it exist. This function will, again, return no value because it's just going to print some side effects to the screen. It's called draw, and it takes in the height. Call it n or whatever you'd like. Inside of this function, let's go ahead and consider what our base case is. And I could say if the pyramid is of height 1, go ahead and print 1 brick. But you know what? Even easier, how do you print a pyramid of height 0? You do nothing. So I bet I can be even more clever here and just say if n equals 0, equals 0, then go ahead and just return. Don't return a value because it's void. Don't print anything. If you want a pyramid of height 0, you got it. I don't have to do any work whatsoever. If I really want to be careful, I can say if you somehow do something crazy like give me a negative number, I'm also not going to do anything because that makes no logical sense. But that's just more of a finer detail. How now do I print a pyramid of height n according to my logic from earlier? What would you have me print first as a pyramid of height n?
1.
Again, it's kind of circular logic, but how can I print a pyramid of height n? I think I can draw a pyramid of height n minus 1, right? Which doesn't even seem logical because I haven't even solved the problem yet, it would seem. But if, again, you believe me that a pyramid of height 4 is really just a pyramid of height 3 plus one more row, that is what I've expressed thus far. Print a pyramid of height 3 but now I have to print one more row. Well, the one more row is actually trivial. Why? Because when I have a pyramid of height 4, what should the width be of the bottommost row? 4. So it's nice. N equals N. Like it's exactly what we want. So I can do this pretty mindlessly in code. 4 int I equals 0, I less than n, I plus plus, and then in this for loop, I think, in this for loop, I can just print out a single hash mark, and then at the bottom of that, I can print out a new line. So weirdly, and let me add my prototype up here, void draw int n semicolon. Let's focus on the draw function here. I feel like I haven't even solved the problem that you asked me to solve. Like, one, I plucked off this arbitrary problem, like if you want no pyramid, fine, no pyramid it is, return, without doing anything. Then I'm sort of cyclically saying, well, if you want a pyramid of height n, well, just go draw it yourself as a pyramid of height n minus 1. But then the last thing I'm doing, and this is where the magic actually happens, I am also saying, once you're done doing that other thing recursively, give me one final row. And where this works out logically, if you sort of reason through this in your mind, suppose you want to print a pyramid of height 4 initially. Well, this does not apply, because 4 is bigger than 0. This does apply, so you print a pyramid of height 3. That puts you logically back in this function. How do you print a pyramid of height 3? Not applicable. Well, you print a pyramid of height 2. Then we get back here. Doesn't apply. How do you print a pyramid of height 2? Well, you print a pyramid of height 1. Okay, let's go back here. Doesn't apply. How do you print a pyramid of height 1? Well, you print a pyramid of height 0. That gets us back into here. Now this applies, and I do nothing. So it rewinds logically in your mind if following along, and I just said to print a pyramid of height 1, I first print a pyramid of height 0. Okay, did that, didn't require much effort. What do I then do? Then draw one more row. And if n at this point in the story is indeed 1, this for loop is designed to print one hash. Then the function will end, and if you rewind in your mind's eye, how did we get there? Well, I asked to print a pyramid of height 2, but I first asked to print a pyramid of height 1. But all I have on the screen is a single hash. But I add another row to that, and if n equals 2 now, that gives me 2 hashes. Then this finishes. Now we rewind again. Now I print another row, 3 hashes. Now this finishes and rewinds. Now I print the 4th row. So sort of in this weird mind-bending way, by not answering the question, but sort of kicking the can down the road by saying, no, you go do this, so long as you take one bite out of the problem, one row, it logically all just kind of works out in the end. So if I haven't made any typos, let me open my terminal window here, make recursion, /recursion, let's do height 4, it actually does work. Let me make my terminal window even bigger and do it again, /recursion 12, it does actually work. So, which is better? Well, in some cases of solving problems, it just helps to write code recursively when what you are trying to do itself is recursive in nature. And even though you probably haven't thought about any of the pyramids in Mario as being recursive, they actually now are. Because again, a pyramid of height 4 is just a pyramid of height 3. It's just a pyramid of height 2. It's just a pyramid of height 1. It's just a pyramid of height 0, plus one more row, plus one more row, plus one more row, plus one more row. We'll see future problems wherein the data structures we're using in the computer's memory are sort of laid out two-dimensionally. Those kinds of problems, too, may very well lend themselves to recursion, even if you can also use iteration or for loops as well. Recursion is such a
problem set 1 हमने किया था उसमें हम इतना करने के बजाय जैसे कि -4 से चालू किया, ठीक है, उतना लाइन को प्रिंट करेगा, ठीक है, -4 फिर 3 -2 -1 फिर -0 1 2
technique, but a challenging technique in the real world that there's even little Easter eggs out there. In fact, let me go ahead and give me just a moment to pull up a browser and then I'll switch screens. If I pull up, say, Google here, any old Google window, and you want to learn more about recursion, so recursion enter, you'll notice this little Easter egg that the geeks at Google have had latent in google.com for years. Does anyone see the CS joke at hand? Yeah? What's that? Yeah, it's asking you, did you mean recursion? Well, I'm pretty sure that's what I typed, so ha ha ha, let's click recursion. Now we're in night mode for some reason, but did you mean recursion? Ha ha ha. Ha ha ha. I mean, that's maybe the kind of laughter it warrants. But like, this is a joke. Like, it's recursion in the sense that Google is telling you to Google recursion again and again. But of course, the second and third results or whatnot are actually real results. But you can try that at home by simply searching for recursion. So again, all it means for a function or an algorithm to be recursive is that if it uses or calls itself. But so that you don't get into some infinite loop like Google, which ironically is sort of buggy and that it will never stop, you have a base case where you just pluck off the easiest of the problems, height 0, height 1, whatever it is, so that the interesting work is left to the recursive calls, where you call yourself again and again. All right, any questions, though, on recursion versus iteration? No? Okay, we've got one algorithm to go because I don't like selection sort or bubble sort yet, even though bubble sorts seem to be a little better with that optimization. My God, even just to sort 100 elements, that code felt very slow on the screen when visualized. Well, let's introduce one other algorithm for sorting, even though there's many more out there. But merge sort is an algorithm that I claim is going to be faster, even though it too will probably by design bend your mind a little bit. It's a little hard to wrap your mind around at first glance, but among its ingredients are going to be recursion. So the algorithm for merge sort is essentially this: 3 lines of pseudocode, which in and of itself sort of hints at the sort of mind bending. Sort the left half of the numbers, then sort the right half of numbers, then merge the sorted halves. So like that is literally merge sort. If you are handed a whole bunch of numbers, like an array of numbers like we were earlier before the break, how do I go about sorting all of them? Well, first sort the left half, then sort the right half, then merge the sorted halves. And the first 2 lines here right, feel kind of obnoxious. Like I ask you to sort n numbers, and you say, well, you go sort these numbers and then sort these numbers. Like I haven't actually given you a solution to the problem, but there's some magic in this last step. Merge the sorted halves. So what do I mean by that? Well, first, let's consider the base case. If I give you nothing to sort, you can pluck that one off trivially. Just quit. If there's only 1 number or heck 0 numbers, you're done. And so that case is easy. But the recursion is clearly manifest in these 2 lines because this is an algorithm called merge sort. And if I'm telling you to sort the left and sort the right, well, you're probably going to use the merge sort algorithm to do that, but the problem's going to get smaller and smaller. So let's focus on what it means to merge 2 sorted halves. So wonderfully, during the break, we replaced the lockers with these here shelves. And on these shelves are 2 sorted lists of size 4. The whole list is not sorted because notice I got 1, 3, 4, 6, but I've got 0, 2, 5, 7 over here. Suppose though I want to merge these 2 sorted lists together, each of size 4, into one bigger list of size 8. How can I go about doing that? Well, this is what it means to merge 2 sorted lists. You point at the first element of the first list, maybe with your left hand. You point at the first element of the right list, maybe with your right hand, and you compare those 2 values. And obviously, if I'm pointing at 1 over here and 0 over here, which is the smaller of the 2? Well, of course, 0. So what do? I take it physically here. I'll light it up for dramatic sake, and I'm going to put it into its appropriate location up here. Now, my left hand is still pointing at the 1 on this list. My right hand is going to move to the right and point at the 2. Same thing. How do I merge these 2 sorted lists, one of size 4, one of size 3? Well, I compare what I'm pointing at, the 1 and the 2. Let me go ahead now and pluck the 1 off and put the 1 at the very top there. Now my left hand and right hand are pointing at 3 and 2 respectively. I compare. 2, of course, is smaller, so I grab this, light it up, and put it up there. Now I'm pointing at 3 and 5. 3, of course, comes next. I turn its light on, and I put it in its right spot up here. Now I'm pointing at 4 and 5. 4 comes next. So I do this. Now I'm pointing at 6 and 5. 5 comes next, so I turn this on and plop it up here. 6 and 7, notice I'm down to 1 element in each list. I'm almost done merging. I pluck off 6. Now I don't have to any more work to do with my left hand. My right hand finishes here, and I have merged the 2 lists together. How many steps did that take? Well, there's 8 elements total, 0 through 7, and every time I made a comparison, I moved my left hand or the right hand. So ultimately, I moved each of the 8 elements once and only once. So that's n steps to merge 2 lists of size n over 2 plus size n over 2. And that's it. So that's what I mean to merge 2 sorted lists. But there is something subtle about what I did here. That was pretty straightforward. Seems pretty easy to merge 2 already sorted lists. But why am I using shelves all of a sudden? This is very intentional. I didn't just use a single table like where we had the lockers a moment ago. Yeah? Yes, I'm not shuffling the numbers around. I'm not swapping things around in the same memory as our humans were. I'm kind of cheating and using some extra space, if you will. Literally twice as much space. I started here, and then I used sort of a separate array that was blank for me, sort of allocated but not used, to store that. And this speaks to a fundamental trade-off we're going to start to see. Almost always in computing, if you want to improve the running time of something, you've got to spend some resource. You have to increase the amount of space, maybe, that your algorithm uses. You have to increase the amount of time that you, the human developer, put into figuring out the problem. Case in point, when I said earlier, sometimes I take shortcuts and I'll whip up a very stupid, simple sorting algorithm. Why? Because my time, I'd argue, is valuable when I'm trying to solve a problem, and I'd rather spend time on other things, so I don't spend much developer time, but that means my code is going to be slower as a result. So space, time, development time, money, any kind of physical resource, energy nowadays is something that you can either increase or decrease and have an impact on these other measures as well. So that's only how we go about merging two lists. How do we go about sorting left and right? Well, for this, let me ask Yulia to join us up here on stage so that I'll act things out digitally on the screen very cleanly. We'll also mimic what we just did here physically with the physical numbers in order to sort an actual list of values that starts off completely unsorted. So the list we're going to do is this, arbitrarily 6, 3, 4, 1, 5, 2, 7, 0. We're going to start with them all on the top shelf ultimately, and we'll see by acting this out how we can go about sorting 8 elements that start off completely unsorted. And the 3 steps we're going to use are these: sort the left half, sort the right half, and then merge the sorted halves together. So those numbers again that Yulia is putting in place are 6, 3, 4, 1, then 5, 2, 7, 0. We have not rehearsed this, so we will see how well we both do together at this. All right, so here is the array of numbers at top, physically represented here. You can look at whichever demonstration you prefer. Let me make clear that this is really an array, and indeed, there's only so much shelf space. Like Yulia can't just kind of steal space over here to the right or over to the left. Like, we are limited in space, but she does have extra space here and technically here and here if she really wants it. All right, how do I go about sorting a list of size 8? Well, what was step 1? Sort the left half. Step 2, sort the right half. Step 3, merge the sorted halves. That's all you have to remember. So here's the original list. How do I go about sorting the left half? Sorry. How do I go about sorting the original list? I go ahead and I sort the left half. So Yulia's kindly going to act this out by just using some additional space. I'll do it digitally here. This now is a list of size 4. How do I sort a list of size 4? Well, I've got an algorithm for that. Sort left half, sort right half, merge the sorted halves. So let's do this. Let's go ahead and sort the left half of this list of size 4. And now, how do I sort this thing? Well, this is now a list of size 2. How do I sort a list of size 2? Sort the left half, sort the right half, merge the 2 halves. This is where things get kind of stupid temporarily. Okay, done sorting the left half, done sorting the right half, but what's the magical third step? Merge the 2 together. How do I do that? Left hand, right hand trick. 6 and 3 are being compared. 3, of course, comes first, and then 6. So I have merged those 2 together. And so now we have a sorted list of size 2, but this is still unsorted, that's still unsorted. So what came next? How did I get to this point? I sorted the left half, I sorted the left half, I sorted the left half, right half, I merged. So what step comes next? Sort the right half of that original half. This is where it's hard to sort of keep track of, but if you take on faith, now I'm going to sort the right half. How do I do that? Sort the left half of that right half. Done. Easy. Sort the right half of that right half. Done. That was easy. Let's now merge together. Left hand, right hand. Which comes first? 1, obviously. So I sort the 1. Or I merge in the 1. Now I merge in the 4. Now, at this point in the story, I've got a sorted left half. I've got a sorted right half. What comes next? Merge the sorted halves. How do I do that? Left hand, right hand. 1 comes first, so I merge that in. 3 and 4. 3 comes first, I merge that in. 6 and 4. 4 comes first. Now, I'm no more right hand, so I merge in the 6. And now, not coincidentally, you see that we have sorted the left half, just like the short demo I did earlier. That was a lot of work, a lot of talking. We still have another half to go, but I'll do it more quickly. Let's see how quickly we can do this. How do I sort now the right half of the original list after sorting the left half? Well, what do? I go ahead and sort the right half. All right, well, what does it mean to sort the right half?
Half kar do usko.
I'm going to go ahead and sort the left half of the right half. All right, what does that then mean? Sort the left half, done. Sort the right half, done. Merge the two halves. 2, and then 2. 2. Okay, good. And then 5. Okay, good. And now the left half of the right half is sorted. Now I sort the right half of the right half. So I got the 7, 0, and I sort the 7, done. 0, done. Now I got to do the merge step, pointing at left hand and right hand. The 0 comes first, then the 7. Now I have sorted the right half of the right half. What's the third step? Merge those two halves. So I point left and right. 0 comes first, then 2, then 5, then 7, and now I've sorted the right half. This is like a really difficult Price is Right kind of thing here. All right, so now we've got we've sorted the left half, we've sorted the right half. What's the final step?
So the left half.
Merge the two halves, and this is exactly what I did before. So dramatically, as the lights come on with each of them, pointing at left and right, 0 comes first, then 1. Okay, what comes next? 2 comes next. Then 3. Then 4. Then 5.
6,
then 6. And a huge round of applause for Yulia if we can, once we hit, and 7. Thank you. Okay. So she and I will debrief as to whether we need both of these visuals moving forward, but hopefully it makes clear that all we're doing is like this mindless, fairly bite-sized problem solving of sort left half, sort right half, merge the two halves. And if we now consider just how much faster or slower that is than an algorithm like selection sort or bubble sort, let's see if we can't analyze this just a little bit. We ended up having an entirely sorted array, but how did we actually get there? Well, if we consider what the possible buckets are for asymptotic running times here, let's consider the sort of breadcrumbs we might have left along the way if I didn't keep deleting things as I went. So we started with these numbers up here, and at one point or another, we did all of this work that's pictured on the screen, even though it only was up on the screen briefly. So in other words, we started with one list, and then how many times did we divide it in half? 1 time, 2 times, 3 times. So sort of we did this dividing and conquering of the entire list 3 different times so we could get to this, like, these leaves, if you will. And even though we'll talk about this more in future weeks, if you've ever drawn like a family tree where you might have like grandma and grandpa and then parents and then children and so forth, it's sort of like an upside down tree whose branches grow downward, where the leaves, so to speak, like the descendants, are at the very bottom of the tree. And that's terminology we'll come back to in the coming weeks. But how many times could we chop up this original array into smaller and smaller pieces? 3 times for each of these elements here. Moreover, how many steps did it take to merge those lists back together? Well, that's going to be the operative question. It turns out that the number of times we were able to divide the original list in half and half and half to get to those very single stupid problems of single numbers was log base 2 of n. You can do a bit of a sanity check here, whereby if you just do the mental math, if we had 8 elements originally, and the answer to this question is 3, well, that actually kind of works out, because log base 2 of 8 actually is 3, which describes exactly how many times we chop the problem up into smaller and smaller pieces. But again, there was some merging going on, whereby we actually wanted to merge those then sorted lists together. So how did we go about doing that? Well, every time we merged, we only looked at or physically touched the number once before putting it into its place. So my hands were constantly working their way through this list, such that when we had the singletons, done. 1, 2, 3, 4, 5, 6, 7, 8. Work was done. When we did this work, it was 1, 2, and then 3, 4, and then 5, 6, and then 7, 8 steps as well to merge those together. Then it was 1, 2, 3, 4, 5, 6, 7, 8. In other words, no matter what conceptual layer of this tree we are in, it was taking me n steps, or 8 specifically, to do that merging. So what that then invites is, what's the total amount of running time involved here? Well, if you're doing n things, log base 2n times, the total math works out to be n times log of n. So that is to say, merge sort, unlike selection sort, unlike bubble sort, is in big O of n log n, which even if you vaguely remember your logarithms, log n is smaller than n, so n times log n is definitely better that is smaller than n squared. So if we consider our sort of cheat sheet here of the possible running times that are common, merge sort is in big O of log n. However, nothing I or Yulia did took into account whether the list was already sorted or not, so it's fair to say that the lower bound on merge sort's running time, even if the darn thing is already sorted, is also n log n. Now, that's not as good as n, but at least in general, it's way better than n squared. But here again is a trade-off. If you want to have this nice recursive solution using merge sort, you might not get a lower bound running time unless we go in and add more pseudocode that maybe does something silly like check the list first, if already sorted, quit. And you just kind of special case it with a conditional, but that's sort of a lower level refinement that we won't bother with today. But merge sort then is in n log n, as are frankly a lot of sorting algorithms that you would use in the real world or use in a library. And so as our final flourish today, what we thought we would do is compare these three algorithms that we focused on: selection sort, bubble sort, and merge sort. In particular, what you're about to see is a visualization of some random data 3 different times. The top chunk of data is going to be sorted with selection sort, the bottom data is going to be sorted with bubble sort, and the middle data is going to be sorted with merge sort. And the goal here will be to actually assess and feel and hear what the difference is when you put a little more time, a little more thought, a little more effort into designing your code not only correctly, but well, and thus efficiently.